presentation per se. I'm going to be talking at a very high level, about a lot of things associated with space exploration. In particular, here's the topics. I hope you can see that. It's going to be talking about the brief history of human space flight. Then I'm going to talk about current and planned human spaceflight programs, and then human spaceflight mission complexity and risk, critical science and technology for deep exploration, and then some concluding remarks. Notice that it's mostly human spaceflight. That's my area. That's the area that I'm involved with, is human spaceflight. And NASA's. Hello? Oh.
Yeah, you can go ahead.
Okay. The Johnson Space Center, along with Marshall Space Flight Center, Kennedy Space Center, are involved with human spaceflight. Other centers, NASA centers, there's 10 NASA centers. So sometimes when you say the word NASA, sometimes you have to be specific, because there's different NASA centers and we do different things. JPL, for example, does robotics exploration. So let me talk about the first thing, brief history of human spaceflight. This is going to be kind of a brief history, but let me begin by talking about the beginnings of rocketry at the very high level. So really going back and tracing where rocketry started was actually with the Chinese in 1300 AD, and they were building rockets more so for military applications, and they did that for a while, and that kind of died out. But fast forward a few centuries, and you have a gentleman by the name of Sir William Congreve. He was an English artillery officer, and he was also an inventor, and he invented a military rocket that used primarily gunpowder as a means of propulsion. But it was very difficult for developing rocketry with using gunpowder. The best range was about 600 yards. Interesting, kind of a side story is that the English bombarded the United States back in the 17th century or so, and the Star Spangled Banner talks about the rockets' red glare bombs bursting in air. Those were rockets. Those were military rockets developed by this gentleman, Sir William Congreve. Now, Julius Verne in the 1880s, he was born in the 1880 to the 1930s. He came up with a lot of science fiction. He was an author and a poet and other things, but he had a science fiction book that got real interesting. It was called From Earth to the Moon. And of course, he was French. He also developed the French movie version of that movie in 1902. If you look it up in Google, Google it, you'll see that video. Let's go a little into another country, and Russia. There was a gentleman by the name of Konstantin Tsiolkovsky, and he introduced the elements of science and technology into his stories of controlling rockets moving between gravitational fields. And so he was somewhat theoretical. And there's a picture of him on the right-hand side, but he came up with a lot of interesting ideas. Now, in the same time frame, roughly, we had a gentleman in the United States by the name of Robert Goddard, and he's considered the father of modern rocketry. Now, what he did was he recognized potentials of rockets for atmospheric research and ballistic missiles and space travel. There was skeptics that says you cannot travel in space because there's no air. And of course, they didn't know about Newton's second law, actually, force equals mass times acceleration. And he was the first to scientifically study, design, and construct the rockets needed to implement those ideas. And then the Germans, influenced by space pioneer Hermann Oberth, developed the V-2 rocket. And of course, one of the persons in part of that development was Wernher von Braun, which was instrumental in the Apollo space program. He did not want to participate, as the story goes, in developing weapons for war. He was more interested in spaceflight too, but the only way he could get funding was to participate in these military research and development. And so, he came up with a lot of the ideas of rocketry using the V2. Fortunately, that they developed this kind of late in the war, and of course, they lost, and a lot of the German scientists and engineers, when they had to surrender, a lot of them wanted to come to the United States. And fortunately for the United States, Wernher von Braun was one of the engineers that came to the United States. So let's talk about the first spaceflight missions and programs. Mercury was obviously the first one back in the 60s. And it was the primary objective was to orbit a manned spacecraft around the Earth. We didn't know what it was going to be like to send humans into space. It's never been done before. The first mammal to go into space was a dog, a Russian dog by the name of Lakita, if I recall correctly. And so we had no understanding of what happens to a human in space, how they can function in space. There was a concern that they couldn't eat in space because of microgravity. The food wouldn't go down to their stomach. And of course, we wanted to be sure that we could recover both the man and the spacecraft safely. Now, you see the picture there of those 7 astronauts, and they call them the Mercury 7. Interesting enough, they were all, talk about the qualification for astronauts back then. These guys were military test pilots that basically were flying at the edge of technology and were big risk takers. And so, that's the kind of people you needed for programs such as human spaceflight, where the risks are very high because we were just learning how to do that. To the right of that picture, you see the Mercury space capsule. Then let's go to the Gemini program, the next human spaceflight program, and it was the bridge to the moon. And one of the reasons for that was because it was the first opportunity to fly long duration missions up to 2 weeks. At that time, that was a long time, 2 weeks in space. And the more critical part was rendezvous and docking in orbit, because that was going to be vital for the Apollo spacecraft mission, because they were going to have 2 spacecrafts have to separate at launch into space, separate, and then come back together and dock, go to the moon, let one portion of it, the moon lander, undock, go to the moon, come back up on the ascent module, dock with the command service module, and come back to Earth. So that docking mechanism, even though in the movies it looks so simple, it's not. So anyway, that was a very major one. And of course, they had to perfect re-entry and landing methods, because they were going to be coming in at very high speeds from the moon. And then have to understand, the longer space flight effects for the astronauts. And there at the bottom, you see the Gemini launch vehicle. Gemini had something like 10 launches. And of course, one of the astronauts on Gemini 10 was Neil Armstrong, which was the first man on the moon. And they almost lost that mission. If it wasn't for Neil Armstrong's being calm and his abilities, they would have lost both astronauts. So let's go to, let's see here. The next one, which is the Apollo space program, which probably many of you are already familiar with or seen pictures of. There's the launch of the Saturn V, which Wernher von Braun was obviously the designer and architect of it. And there were several objectives for that particular portion of the program, and that was to establish the technology to meet other national interests in space. There was talk about different things of using space for different applications, and certainly the Apollo program and the technology developed for that was going to be instrumental in helping meet those goals. And we wanted to achieve, basically being the top in space for the United States. And of course, at that time, we had a Cold War with Russia, competing with who's going to be the first to land a human on the moon, and then carrying out a program of scientific explorations on the moon and developing human capabilities to work in the lunar environment. But the Apollo space program program was very complex. It was a very complex system, and I'll mention a little bit more about complexity later in my presentation. But we had
I think some
or
issue.
rather the Apollo 1
Okay.
had,
I think your video was gone for a while.
let's see, did I lose you all?
Yeah, now it's okay. It's working.
Okay, all right, good. So continuing on, the Apollo 1 fire, there was, a lot of contributing factors. And you can talk about, pressures and complexity and whatever. And of course, complexity will sometimes introduce mishaps or hazards. And so what had happened was it was the wiring that was used on, especially for the power systems, could get very hot, and so temperatures that this wire would reach required the use of Teflon, and Teflon had been used for many programs, and it was very successful. However, the way it was placed in the Apollo 1 module made it so easy to get stepped on, especially on the ground. And Teflon was not very good about handling stress and being stepped on and things of that sort. So the wire was braided, and so when they powered it up, there was an arcing. There was the arcing created in a explosive environment because the capsules, space capsules at that time were 100% oxygen. But we've always used oxygen, and so there was always this confidence that there was nothing wrong with that. But you put oxygen and some kind of spark, and you create a major explosion. To the right, you see the picture of the Apollo 13. And that was the most successful failed space mission because obviously, they had the explosion of the command service module, and there was a lot of events that led to that explosion in space, and we almost lost the crew. But a lot of quick thinking and what have you resulted in returning them safely. There were a lot of lessons learned from that program as far as increasing safety in human spaceflight. But here again, human spaceflight is not easy. It's challenging, and you just have to be cautious when you're developing systems especially for human spaceflight, because losing humans in space is not a good thing. Now, fortunately or unfortunately, however you want to say it, we have never lost. In the Apollo program, we did not lose people in space. We lost them on the ground. Now, the next program was the Space Shuttle program, the major program. And that's when I started to work at the Johnson Space Center. It was the first reusable spacecraft, and the concept was to make space accessible frequently. And, basically they called it a pickup truck that could go into space and come back. It was sold kind of very optimistically. They were talking about 100 flights a year and things of that sort, and it wasn't going to take a lot of people to maintain it on the ground. There was pictures of, like 25 people in a hangar, kind of like a jet hangar, aircraft hangar. Complex that it required somewhere around 20,000 people to maintain and service it on the ground. It was a very complicated ship to maintain, and it was very expensive. The operations cost for shuttle ate NASA's lunch. Literally, it costs a lot of money to operate the space shuttle. That was kind of a lesson learned in that. And of course, unfortunately, we also had tragedies in the space program. Not necessarily in space, but in attempts to fly the Challenger in 1986 due to the coldness and You see that little red circle there?
Yeah.
That's basically when the shuttle launched. The solid rocket motor, there was a seal that did not, that became very brittle at cold temperatures and did not seal the solid rocket motor. And as a result, there was a separation explosion of that SRB, solid rocket booster, and it hit the main engine, rather the external tank, and then everything just went into a spin and fly, what they call flight dynamic instability, and it exploded. And right below there, the Columbia 2001, that was due to a foam strike on launch. And it's a long story on that one, but basically, we lost 7 astronauts in both the Challenger and the Columbia accidents. And again, there's a lot of issues that led to that, but in the end, it's about flying spacecrafts is a difficult and challenging and risky business. So let's talk about the space station. So space station is currently operating right now, and so it's a huge facility, about 300 feet long, and it provides international. It's an international laboratory for doing experiments. We got about 16 countries participating in the space station. Microgravity environment provides opportunities to conduct experiments in astrobiology, astronomy, physics, and other. Right below there, you see a picture on the left-hand side of a candle, how it is on a 1G environment, and the same candle in the microgravity environment. You notice kind of a big difference here. Of course, the candle on the left-hand side is associated with what they call a gradient, gravitational gradient. That's why the flames are going upward. And then on the right-hand side, there is no gravitational gradient, so it becomes this oval shape, which I found kind of interesting. But they study fires in space because that's something of an issue, or can be an issue or concern in the flight environment. Primarily because they can't evacuate like we can here on Earth. There's fires just come out the door, and you just can't do that in a spacecraft environment. It takes a while to put on a spacesuit and get outside. And so then there's also conducting technology experiments too, and trying to see what kind of technology we're going to need for future space missions, and also how to improve that technology from a reliability standpoint. Conduct human behavior and health experiments. Down there at the right, you see Scott Kelly. Scott Kelly spent about 340 days on the space station. And you say, well, that's a long time, but you talk about a Mars mission. Mars mission is like 3 years, so he only spent like 1/3 of the time for a Mars mission, and he had a lot of issues coming back. I read a few stories about what happened to him afterwards, and it's dealing with the microgravity environment. Our bodies were not intended to operate in a microgravity environment, not easily. So he had issues with eye vision, cardiovascular, and just a whole bunch of things. If you Google Scott Kelly telling the story how he felt afterwards, it's kind of interesting. But he volunteered because he knew we needed to find answers to some of these long duration space flights, and what kind of technology are we going to need for sending humans in long duration space flight missions. So commercial crew program, and that's something I'm involved with right now, and it's first ever commercial space program. Past space programs, it was all NASA government that basically had ownership of the systems that were developed by commercial companies. And this is now an opportunity for commercial companies to own their own systems they develop, of course, with NASA's help. And it's an opportunity to open a new world in the commercialization of space. And right now we have two that are competing for some contracts for sending humans to the space station. We have SpaceX and Boeing, and of course, right now SpaceX has the lead with Demo2 mission, which I'm very honored and had the opportunity to work that program. But it's going to provide space transportation to the space station. But it's also an opportunity to partner in the Artemis program, and I'll say a little bit more about that later. But the Artemis program is basically the Apollo space program of the 60s, but now in this generation. There in the middle is the Dragon 2 approaching space station and Demo2 mission. And right below there, that's the part that I was involved with, was the what's called the control panel. It's that fancy three-screen touch display that I was involved with SpaceX in developing. And of course, SpaceX is looking at concepts on, like, for example, the massive rocket that they're developing for going to the moon, and providing a one launch vehicle for sending equipment and humans to the moon. And also there in the middle is Blue Origin's human lander. And Blue Origins has teamed up with Lockheed Martin and Northrop Grumman in developing that other human lander. So we got a lot of participation from the different companies. And I think as we progress in the Artemis program, and more specifically for the Mars mission, we are going to need international help big time. It's no one country can do that by themselves. So Artemis program, as I mentioned, this is basically the Apollo program of the 60s in today's time. So interesting enough, our NASA administrator, Brandenstein, is he mentioned this at a presentation at a conference I was at, that he said he's the first NASA administrator that was not born during the Apollo program. And so he is kind of like the new generation of administrators, because the Artemis program is going to be, he's going to be part of a new Apollo program. And so he's very honored and privileged to be part of that. But what you're seeing here is kind of a timeline of what's going to be going on from 2020 to 24 to 2024. And so we have Artemis 1. It's the first human spacecraft to the moon in the 21st century. Of course, that's coming up pretty soon, next year or two. And then first humans to orbit the moon in the 21st century, with Gateway being kind of like the Gateway is, we can call that the moon space station, if you will. And then Artemis is the high-powered solar electric propulsion system that we're going to be experimenting and demonstrating in the moon environment. And then the first pressurized module delivery to Gateway. And then afterwards, human landing systems, to land from Gateway down to the surface, and then we're going to have people on the surface of the moon. So this is kind of a picture, if you will. This is sometimes concept of operations that shows pictorially what's going to be happening over time. So deep space mission operations. Right now, our current situation is, we got the space station there, and with space station, we have a whole bunch of people supporting space station from different countries. At the Mission Control Center, we have folks that are, see if I can get the laser pointer. So we have folks that at the Mission Control Center here that are basically are called flight controllers for different systems on the space station. But then supporting the flight controllers are people in the mission evaluation room. These are all the engineers and the systems developers that understand the systems very well. So the flight controllers don't have a quick answer. The mission evaluation room will have the answer. And then, of course, you got the Russians too as well in Moscow. And I can tell you that when you're working mission operations, because I did this with a commercial crew on SpaceX, things happen very quickly, and you have to be very decisive. You have to make a decision very quickly. Your mindset has to be analyze the data and make a decision. It's not, well, let me think about it and all this, because things are happening very quickly. So your mindset has to shift from, 30 miles an hour to 100 miles an hour. And it can be a little bit stressful for people that are not accustomed to it. I did some back in the shuttle era, and I still remember it being very stressful. I remember one time a flight controller said, because I was a little hesitant in trying to explain what the issue I saw, and he said, you're going to have to be more thoughtful, insightful, more quickly when you ask for for a request. So that kind of sticks in my mind that those people have to operate in a very fast, real-time environment. Now, future. Okay, so there's a kind of a conceptual, notional picture of the gateway, and the gateway is still going to have basically mission control, and to some extent, it's pretty much not so much different than now. Now, in the current situation with station and mission control, we got about a 250 millisecond delay in communications with space station. On going to the gateway on the moon, we're talking about 1.2 seconds. It's not too bad. I mean, think about the Apollo space program. Apollo space program was able to cope with that delay and still land humans on the moon. If you think about what happened to Neil Armstrong on Apollo 11, we had that infamous 1202 alarm that the computer on the Eagle lunar lander had overload of trying to compute all the parameters and what have you. And so Neil Armstrong saw that the autonomous mode of landing on the moon was not working because they were going to land on a bunch of big rocks and boulders and crash, basically. He turned off the autopilot, if you will, and went to manual mode. And, he found a spot with just a little bit of fuel left that had everybody at the ground very worried that they thought he was going to run out of fuel before he found a good spot to land. So here's a case where the human in the loop was very important. If it would not have been for Neil Armstrong, they could have crashed if it was with no humans on board. Now, when we start talking about adding to the gateway, what they call the Mars transport, we're talking about the delays getting longer and longer because Mars is further and further away. So we cannot do this, what we call real-time mission control, as we do right now, and even on the moon. And we're talking about 20 minutes, 30 minutes, depending on how far the Mars is. And so we're talking now about something called onboard mission control. And what is onboard mission control about? Basically, we're talking about autonomous artificial intelligence, basically having the intelligence, computer system, having the computer intelligence of what the mission controllers do, so to help the astronauts basically in mission critical, especially in mission critical situations. So, but we're talking about a lot of complexity. We're talking about a lot of computing power. And one of the challenges of going into space is the radiation environment and how it affects electronics. The electronics that we use here on the ground don't work very well in space. To some extent, they work well in low Earth orbit, because in low Earth orbit, the space station and everything inside of it, including the humans, are protected somewhat with the Earth's magnetic field. And of course, you also have the protection of the space station shielding as well. But as you go further into space, you're dealing with cosmic rays and deep space radiation that's very high energy and very difficult to stop. And so electronics don't work very well in that environment unless they're built for that. And I can tell you that radiation hardened electronics are very, very expensive. Just to give you an example, a computer board that, let's say, for example, it would be used on a computer on the ground. Maybe that computer board run you $100, $125. If you're talking about similar board for a deep space radiation environment, you're talking about $250,000. So big difference in price, and it's because the electronics were built for deep space radiation. We're going from what we call crew mission control dependent development to crew vehicle dependency, where the crew is dependent on the vehicle onboard mission control for making it happen, for making the mission being successful. So let's talk briefly about human mission complexity and risk. And I'm going to give the Space Shuttle an example. Space Shuttle had a whole bunch of stuff on it. Very complex system. I'm going to give you an example, just one piece of complexity. If you're looking at this, what we call the product breakdown structure, you got the space transportation system. Underneath that is the external tank, the orbiter, and the solid rocket boosters. Under the orbiter, there's one system called the avionics system. That was my system that I was involved with, or the area that I was involved with from my division. Under the avionics system division, there was different subsystems, and one of them command data and handling. If we dig deeper into command data and handling, you got the general purpose computers. These were the flight computers that did all the flight control of the space shuttle. Basically, it was there was something in the vicinity of 1,200 sensors that were being measured and sensed by the general purpose computers. But it doesn't stop there. From the general purpose computer, it talked to different subsystem boxes, one of them being the master event controller. And that master event controller was the one that did all the control for the main engine controller for controlling the main engines. So you can see how complexity can exponentially increase in complex spacecraft systems. But the only way to deal with complexity like this is something called systems engineering. And that's something that I grew to learn on the job, if you will, is to breaking down a complex problem into more easier, manageable problems. And it's not to say that that's not a challenge. It is. It's still a challenge. It's just having good people, good tools, and good processes in place, which I think NASA does for making these projects successful. So let's talk about complexity, hazards, and risks. And so there's hazards in human spaceflight, hazards in system design, hazards in humans, hazards that lead to risks. Okay, so right here I show a picture of some of the hazards associated with the human in themselves, physiologically and psychologically. There's the gravity, the physiological effects, like fluid shifts. There's if you have sinus problems, you get no sinus strain in the microgravity environment. And that's why you see sometimes astronauts' heads look kind of swollen. It's because they're not their sinus are not draining. They have bone loss. Space radiation. There's possibility of long-term cancer being exposed to the deep space radiation environment. You got distance from Earth. Okay, basically we're talking about we're going to have something like autonomous medical doctors on board, to help them, because there's going to be potential issues that they're going to have to deal with from a physiological standpoint. They're dealing in a hostile closed environment. The vehicle design is going to be important, making sure that they stay safe in the basically the environment of deep space. It's very cold. It can be very hot, and of course you have no air outside. So your vehicle design is your little world, and it's got to protect you. And of course you got to deal with toxic exposures, making sure that no toxics are released into the closed environment. CO2 levels very important, because we take out CO2, but if there's no way of recycling that can become an issue for our body. And of course, one of the biggies is isolation and confinement, the behavior of being away from home, far away from home for a long period of time, missing your family and your and your loved ones. And so, how are you going to deal with that situation? I had an opportunity to talk to a Russian scientist many years ago, and he said that a lot of the isolation and confinement experiments that he did in Russia, in Siberia, he said that after some of these guys that were in there for over a year in Siberia and whatever, they would come out and they would talk about what made them survive for a long period of time, and in all the cases they pretty much said the same thing, talking about good eating and staying active and all that. But one particular person told the Russian scientist, he said, the main reason that he survived lasting that long was that he knew he was on Earth, and he knew one day that door was going to open and he was going to get out. So he had that mindset that, hey, I'm still here on Earth and I'm going to get out. Not the case for Mars. They're going to see Earth as a tiny little dot. How's that going to affect them? We're not sure. System complexity. Here's a picture for those of you that love mathematics. Is some of the interactions that happen with whether it's a human or systems. Okay, so each one of these circular bubbles can be a human or it could be a component in a system. And of course, you can have a component in a system talking to a component in another system, and that other system has other components and interactions. So what's happening here is that the more interaction that you have, the more interfaces that you have, the complexity goes up dramatically in communications, whether that communications is verbal or that communications is digitally or the communications is, let's say in a thermal fashion or whatever, but you have an interaction that you have to take into consideration because of more interacting elements. And that's basically what this is trying to show, is how complexity increases over the amount of interactions. Regardless of what that interaction is, there's still a complexity involved there that you have to take into consideration. And again, going back to what's called systems engineering, that's one of the challenges, is managing the risk and complexity that can happen when you're developing complex systems. You're trying to manage the hazards and you're trying to manage the risk. And complexity makes it like that. You've overlooked something. It's a possibility that you overlooked something. This came from a professor from Yale, Charles Perrow, that in essence what he's saying here is that if you're not developing a complex system correctly, you could create a mishap or an accident. All right, so let's talk about real briefly the human needs on the moon and Mars. So physical needs, obviously they got to have water. We as humans, we need water, air, food, warmth, sunshine. Sunshine, obviously, to maintain circadian rhythm so we can sleep properly. Exercise our muscles, make our bones strong. In a microgravity environment, our bodies tend to respond by saying, hey, I don't feel that 1G environment, 14.7 pounds per square inch. I don't have to produce calcium. And so what happens is your bones become brittle. Closing, buildings and habitats. We got to make sure that the buildings and the habitats that we build for these humans are going to be large enough. Confinement is something that humans don't particularly like. If you know the word claustrophobic, some people don't like to be claustrophobic in a very small environment. Obviously, we got to keep them healthy. In technology, that's going to be a biggie. Electricity, how much electricity to produce, materials, tools, computers and communications, the different vehicles that are going to be needed, and the fuel, the robots, and all this must be highly reliable, because as I go here into the psychological needs, going back to limited space is going to be important. Isolation. Okay, here's one related to highly reliability, safety dependence on machines. I was reading some articles associated with how unreliable systems can affect you stressfully, and that stress can translate to a human that's not operating properly, dealing with situational awareness, where situational awareness is basically comprised of perceiving something in the environment and comprehending what's going on in that environment, and then deciding what to do in the future based on what they're seeing. So if you're stressed out, that situational awareness may not work properly. Group dynamics, working with different astronauts and different belief systems, different, from different cultures. Leadership is going to be important. Crew selection, obviously, going to be it's going to be important in group dynamics and leadership. Adaptation, adapting to the different situations that are happening. And of course, the big one would be communications with loved ones to keep you psychologically healthy. And so complexity can lead to human limitations and mishaps. I just spoke about the Apollo spacecraft that we lost the 3 crew members on the Apollo 1 fire. And there I'm mentioning about the Teflon coated wire that I mentioned previously, and they could handle the heat, but not the wear and tear. And then Spaceship 2 was kind of an interesting one because the flight mishap was a combination of technology and the lack of factoring the human element into the design. So what had happened was there's something called feathering, and it has to do with these feather flaps that are released at certain time of the mission. And so these feather flaps are supposed to release at 1.4 Mach speed. And what happened was one of the crew members released it at 0.8 Mach. But there was nothing in the system to indicate to the to the flight crew that this is too early. You cannot do this. Prohibited. It basically, the system allowed them to create that error, and as a result, the system crashed. So this is an example of a mishap that can happen in complex systems. And especially if you fail to take into consideration the human. As engineers, we're trained in school to become good hardware and software designers. But I can tell you from my experience in training, and even talking to engineering students now, they get virtually no training about understanding the human element. And in human design, whenever you're dealing with a human, you always have to factor the human element into the system, because you can have the perfect hardware system, you can have a perfect software system, both operating, flawlessly, and then you bring in a human that doesn't understand how to operate the system and punches the wrong button at the wrong time, the system fails. So you can have a failed system despite the fact that you had a perfect hardware and software system. Of course, hardware and software are very deterministic. You know how it's going to operate because the person designed it. But the human, not so much deterministic. There's so many variables in the human, and that's one of the challenges of human spaceflight. That's why one of the reasons I got interested in the human element design, and that's why, as Samir mentioned, I was one of the founders of the Human Systems Integration Employee Resource Group to bring an awareness of this into the NASA culture. And of course, we're very proud to say that we've included the human systems integration into a lot of the NASA documentation. And I just learned recently that the Artemis program has a human systems integration plan in place. So I'm very pleased that we're starting to do more and more of that. Human systems integration is not new. It's been around a long time, but we can always improve on what we've done previously. All right, so critical science, technology, and deep space exploration. So for the moon, there's explore the hidden reserves of water. There's water that's been detected, and we need to further do research on that. There's a lack of a dynamic surface on the moon. So basically what this is saying is that the moon it's not changing and churning like the Earth is. At one time, both the Earth and the moon were bombarded many, millions of years ago, and maybe billions of years ago. And but the thing is that the moon pretty much kept a lot of that in place because it has no atmosphere. It doesn't have the dynamic changing surfaces like the Earth. The Earth, we got volcanoes, we got earthquakes, we got oceans, we got winds, we got hurricanes, we got cyclones, typhoons, all that. And that's altering everything. And so it's very hard to find all this bombardment that happened centuries ago. But on the moon, because nothing changes like that, we can find that very quickly and see what happened billions of years ago that maybe happened to the Earth also as well. And of course, to live and learn on another planet. For Mars, there's a picture of Mars and a picture of the United States relative to the size of Mars. I suspect Africa would be much bigger. I think Africa is much bigger than the United States, so maybe it would encompass all of Mars. But anyway, that's just a kind of a picture representation of the size of Mars, and we want to determine if life ever arose on Mars. Characterize the climate of Mars. One time they think Mars had climate. What happened to it? What happened to the water? Where is it? Underground? Characterize the geology of Mars. And of course prepare humans for exploration of Mars. You can have the best robots in the world, but the human has more creativity and more what do we call resourcefulness of trying to figure out ways of investigating what is on Mars. And the thing about Mars is that if you think about the Goldilocks zone of solar system, Goldilocks zone being the area where planets can harbor life. Mars is on the outer edge of the Goldilocks system, Earth being right in the middle of the Goldilocks, and Venus being on the inner edge of the Goldilocks zone. So there's a lot of things that we can learn about Mars, and once humans go there, but it's going to be challenging. The Mars expedition, talking about deep space testing, is going to be the proving ground for some of the technology just to take us there. We need to first make sure that our spaceship can go out to Mars and come back to the moon safely without landing people on the moon. And then once we do, then we will have a way of entering the Earth's, the Mars atmosphere, very small atmosphere, and land on there and communicate back to Earth what we're seeing and what we're doing, and then start establishing a habitat with humans on there. And so why send humans to Mars? Well, we have a quest to explore. We've been explorers ever since the days where all we had were our feet to walk. And, we always wanted to know what was on the other side of the mountain. So we, packed our things and walked on the other side of the mountain. We came to the edge of the ocean, and we said, what's on the other side of the ocean? Well, let's build ships to go on the other side of the ocean. And then we saw birds flying, and we wanted to build planes just like to fly like birds. And then we looked at the stars, and we're building spaceships to go to other planets and hopefully outside of our solar system one day. So we're explorers biologically. We're driven for innovation, and technologies that probably have applications here on Earth as well as space. Answer the questions of life on other worlds. I mean, it'd be great to know that life existed, or maybe does exist, on other planets, and just in our neighborhood of Mars. Mars is the best choice right now, given the distance, for learning to colonize on another planet. It's close to Earth, sort of, somewhat. The warmth and light, to some extent, the length of the day, close to the Earth, has seasons like Earth, and it has somewhat of an atmosphere, water, and metals. But again, it's the challenge of going that far. We don't know how to live on another planet, and that's why going to the moon is going to be important, first and foremost, to learn how to live on another planet. We just don't want to go straight to Mars. There was many years ago the thinking of going to Mars first and not going to the moon. They said, we've been to the moon, been there, done that. Not true. We've been there, done that, but we've only spent something like, what was it? Somewhere in the vicinity of 13 days total time on the moon. And so we don't know how to live on another moon. We don't know how to take the resources on another planet and create things that we can use for humans. So, like, for example, growing plants and things of that sort, getting water and stuff like that. So there's still a lot of challenges there. And, one of the things about Mars distance, just to give you an example of, taking humans to Mars, is that, the distance can be anywhere from 34 million to 140 million miles. And spaceships typically travel 300 million miles in about 8 months to reach Mars. Um, but one of the challenges is landing something on Mars coming from the Earth. And here's an example of Mars Curiosity. And talking to some of the systems engineers, I happen to have had the opportunity to work with one of the systems engineers that became the systems engineer on the Mars Curiosity. And that particular person told me that the weight of the Mars Curiosity, which is about 2,000 pounds, is about the limitations of landing something that big on Mars from Earth. And, we're talking about trying to land huge things on Mars from Earth. And so we're going to have to come up with better ways of landing large spacecrafts bigger than Curiosity on Mars. And here's a kind of a landscape, and I won't go into a lot of the details of it, but it gives you an idea of all the development that needs to be done, to make a lot of this happen. We're talking about propulsion systems. We're talking about in space. Robotic systems, telerobotic systems, communications. We're talking about human destination technology, like, for example, in situ resource utilization that takes the soil and creates, gets water out of the soil and even conditions the soil so we can grow things. Nanotechnology. It'd be great if we can develop technology that does self-repairing structures. There's going to be some accidents along the way, maybe meteoroid hits, and so perhaps we have to have a structure that detects a failed portion of the structure and repairs itself using nanotechnology. Modeling and simulation, trying to model and simulate a lot of the stuff early on before we build things to see what it's going to take to build it, and basically try to save some money early on in the program to making sure that what we're developing is going to work. Thermal management systems, that's going to be huge in dealing with all the heat that's going to be created with all the systems that are needed just to provide life support for a human. That's one of the reasons why human spaceflight is very expensive, because of all the things that are necessary to protect the humans from the space environment. So a lot of challenges here, but obviously there's a lot of work to be done, and I'm sure there's going to be a lot of countries, and I hope India gets involved with this too as well. We're developing some of this technology. We just have so much in our plate, so to speak, in developing technology, and particularly dealing with the human element. So, conclusion. I have here a note that says, remember that life can be a challenge. You are not defeated until you stop trying. I know maybe you're going to want to pursue maybe coming to work for NASA, or just becoming an engineer or scientist, and maybe a doctor, and all those are very important. But you are not defeated until you stop trying. And so one of the things that I also share with students is some of the things that you should also take into consideration. Learning science, technology, engineering, and all that, that's great. That's all the technological stuff. But there's also the human side, and the human side I find just as important as I do the technology. So, practice gratitude daily. Give back, become a mentor. I do this. I've been doing this for years, and I love doing outreach. And all this looks great in your resume. If you're a university student applying for a job, and let's say you're a 4.0 in engineering, but so are other 7 applicants that are 4.0, what do you think is going to make you different than the other applicants if they're all 4.0? So it could be that you've done a lot of volunteer work, you've done outreach, you've done things to help make lives better for people. That's a big plus. It says a lot about the character of you. And you'd be surprised how some recruiters are looking for that. They're looking for a balanced person, the balance in technical and a balance in the human skills. Get out of your comfort zone. Just don't learn one thing, but start learning multiple things. That happened to me as a double E. I started learning about vibration structure systems. I started learning more about thermal systems, even though I took courses in school. I learned a lot of that on my own, just to become more familiar with what it takes to build spaceflight systems. And then something that I always share with students is even though I work for NASA, they say, "Oh, you must have been a 4.0 in school." No, I wasn't. I have to consider myself an average engineering student that struggled with tests. I hated taking tests, uh, and I started to learn after I started coming to work for NASA that in the end, it's not so much the grades, but it's your ability to take what you have and learn and adapt, innovate. And this is what's going to help you become successful. And I've developed a few systems over the years and gotten a few patents along the way. And it doesn't reflect the grades that I got in school. And the grades in school were determined by a professor that had a certain philosophy of teaching the material to the students, and some students catch on better than others. And I was one of them in some classes that I could not catch on because the way it was taught, it was too theoretical. I was more of a practical person. And the best tools is very cheap for creativity. Take a peep at a pencil, paper, and a quiet environment, and you'd be surprised all that you can do. All right, that is it, folks.
I think that was really a good session, and the last slide specifically must have inspired all of us, especially the kids. So, yeah, some of the questions which I have already shared with you earlier. So, maybe we will just go through them one by one. So, the first question is
Sure.
uh, what is the importance of cryogenic fuel in working of rocket, or are they just a fiction, or could it be real?
So cryogenic fuels, again, I'm not a propulsion guy, but I know that it's been around a long time. I know shuttle uses it. I know that Ariane 5, the French vehicle uses cryogenic fuel. Obviously, you're basically taking fuel and lowering it to a temperature that becomes liquid fuel. It was used in the Apollo space program. The main engines of the Saturn V used cryogenic fuel. So it's very real. And obviously, one of the importance of the fuel is because it has a high amount of energy per. I forget the term is used. Impulse, specific impulse. So it's real, and it produces a lot of bang for the buck. But of course, that's a chemical engine, right? So we need to look at other different kinds of engines, and we are looking at different kinds of fuels. We're looking at, like, for example, Vasimir being developed by former astronaut Franklin Chang Diaz, which is using plasma as a way of propulsion and taking us to the moon, or rather Mars, in about 30 days versus 8 months. So anyway, yes, cryogenic fuels, very real and very important for the space program.
Okay, good. So the next question is how fast a human can travel in space without sustaining any injuries? I mean, it is, I think, more of comparison to whatever we see in Hollywood movies. So from one dimension to
Okay,
another,
so how fast can a human travel in space without sustaining injury?
yeah.
Okay,
Yes.
so here's the thing. Yeah, interesting. A lot of these are somewhat related to physics. So if you can travel as fast as the vehicle that you're in is traveling. So, and to give you an example, I know many of you perhaps have, obviously been in cars and you're going 50, 60 miles an hour. Well, you're sitting inside the car, how fast you feel you're traveling if you close your eyes. Well, sometimes, if it's a smooth road, you don't feel like you're traveling 50, 60 miles an hour. And because you're going the same speed as the car. So and of course, astronauts right now on the space station, they're traveling 17,500 miles an hour in an orbit. They call it the orbiter velocity. And so they look like they're not moving very fast, but they are. They're moving, but so everything is moving. So they call it the relativistic framework, if you will. So in theory, if you can get a ship to go the speed of light, you can go the speed of light too. Here's where the injury can happen. The injury happens when you decelerate. Okay, so if you're going very fast and then you decelerate, that's where you can injure yourself. Here's a case in point. You're going 50 miles per hour. Your body's going 50 miles per hour. Your organs in your body are going 50 miles per hour. You hit a tree. What's the speed of the car now? 0. But you were still going 50 miles per hour. So you impact the car, the front dashboard, at 50 miles per hour. When your body hits the dashboard at 50 miles per hour, your organs in your body also hit the internal portion of your body at 50 miles per hour. There's where the injuries happen. So it's not so much the speed that you're traveling, it's the acceleration and deceleration. Acceleration, you could get hurt too as well. I know in Star Trek, we talked about when they go warp factor 2, basically twice the speed of light. Well, if you don't have a way to dampen that acceleration, you would basically hit the back of the spacecraft and can potentially die. So it's not so much the speed that you're going. If you're going at a steady rate, it's the acceleration and deceleration where humans can get hurt.
Okay. Yeah. So next question which I will take up is before the launch or even demo 2, what type of training is given to the astronauts or cosmonauts?
Oh boy, there's a lot of training associated given to the astronauts before launch. I mean, they start training, oh gosh, sometimes years before. I know astronauts were already training on the displays like 3.5 years before this launch, but they also train on the systems. Yeah, they learn everything about the spacecraft. And so the training is just not how to use the system, but understanding the system and the behavior of the system. And that's important because understanding how the system works and the behavior of the system, basically going back to what I mentioned earlier, situational awareness. So situational awareness, again, perception of an event, of something going on, comprehending of that event, whatever's going on, and then projecting in the future what you need to do. So you have to have good situational awareness of the spacecraft. In order to do that, you have to understand the spacecraft and its behavior very well. So it's just not the training of using the system, but understanding how the behavior of the system works. So, there's a lot of training. And they learn about the orbiter mechanics. They learn. I mean, it's just basically a whole bunch of training. I know on shuttle, because Space Shuttle had 2,500 switches on there, astronauts would start training like 5 years before a mission. So, but they had to learn everything about the space shuttle. Again, going back to situational awareness, and then there's another. The reason of training so that one astronaut knows what the other guy is doing, and it's called, basically watching his back or her back, is seeing what they're doing is consistent with their mental models of how the system is supposed to be operated. So lots of training, making sure that they've reduced human error down to nothing.
Yeah. So I won't take much time. So I just have two more questions. The next one, I think every kid or participant is going to ask this. How can I join NASA as an engineer or a scientist, despite the fact that I am from a different country?
That's a tough one. If you're trying to join NASA in the United States to be a U.S. Astronaut, it's a challenge being from another country. Obviously, the minimum requirements for NASA, United States astronaut, is to have a bachelor's of science in a STEM degree, science, technology, engineering, or mathematics, and then there's well, you have to graduate from an accredited university, and then of course U.S. citizenship, and then there's a whole bunch of other things that come into play but are not necessarily advertised as required. Like, for example, a lot of astronauts are Eagle Scouts. So if you're familiar with the Boy Scouts, being an Eagle Scout, you're at the very top of being a top scout. Playing instruments, you'd be surprised how many astronauts were chosen for some of the things that were outside of their technical area. You know, all the astronauts that apply pretty much are just incredible people with incredible grades, incredible backgrounds, you know, 3-4 degrees, 2 PhDs, you know, et cetera, et cetera. But sometimes NASA looking beyond the technology. Remember I mentioned about the human element. They're also looking about the human aspects of it. I know one astronaut that I've worked with on crew displays. And one of the things about him was he was a medical doctor, but he was also a certified machinist and also a welder. And he also plays violin. And so, you know, it's just incredible what these people do. But going back to your question about being a foreign student, or being a foreigner and then trying to join an astronaut, you know, one of the things that's going to be of interest is it may be easier, especially here in India, that, you know, India's looking at the human spaceflight program. So there may be opportunities for some of the citizens of India to, you know, to pursue becoming an astronaut in the Indian space program, ISRO, I believe it's called. So, I think that'd be a much easier. I have to share with you a story of a young lady that I became a mentor from India, and you know, she was in high school when she reached out to me, and at that time she wanted me to evaluate a report about a quadcopter on Mars, and so, you know, we started to talk and collaborate and whatever. And then she wanted, you know, she wants to come work for NASA, not necessarily as an astronaut, but she wants to work as an engineer. And so she asked me, you know, what's it going to take for me to, you know, to become a NASA employee engineer? And I told her, you know, it's going to be a hard route. You know, first of all, you know, you have to get your citizenship and get your engineering degree here, probably from the United States, better. And so she said, okay, I'm going to do that. So fast forward. You know, she got a degree, a bachelor's degree in India. She transferred to Syracuse University in New York, in the United States, to work on a master's in computer science. She graduated from there, and then she was able to land I guess she got a PhD offer from Caltech in California in the United States to pursue a PhD in the area that I had suggested to her was machine learning and artificial intelligence. And so my understanding the last time I communicated with her was that she was going to be working for a professor that happens to work for the JPL, Jet Propulsion Laboratory, which actually is part of NASA. So she has taken a lot of steps to eventually, perhaps one day, landing a job at NASA. But it's a long road, and it's not simple. But again, as I mentioned, you know, you're not defeated until you stop trying. So that's something you always have to be thinking about.
Yeah, that's correct. So, just last question. This is from my side. So, how do you think this demo two, whatever demo two and International Space Station and whatever collaboration between NASA and SpaceX has been done? So, how this is going to help in the near landing to the moon or the Mars? How this is going to help make us have a future mission?
Well, I think it's definitely opened up a door that says, you know, commercial crew, commercial programs, commercial companies like SpaceX and others that are out there are you know, can do the job of doing human spaceflight. And I have to tell you that you know, there's a lot of creative people in the commercial world, and so I think what Demo2 demonstrated was the ability for commercial crews to develop human-rated spacecrafts, you know, certainly with the help with NASA, and to show that they are good partners to work with for future for space missions, like going to the moon, human landers. One of the things that is also taught at NASA is what we call diversity and inclusion. And so, if you have a more diverse background in people, from different cultures, men, women, just different diversity, it makes for a more stronger, for a more rich environment for developing systems that have never been developed before. So we just can't depend on a certain way of thinking all the time. I think sometimes, and I'm just speaking for myself here, that in the past, NASA has had a traditional way of developing systems, but maybe there's a better way, and that I think that's what commercial companies will bring in into the playing field.
Okay, right. So that's it from our side. So George, I think now you can again have your cup of coffee. So,
oh yeah, here we go.
yeah.
Thank you.
So thanks a lot.
Yeah.
Yeah, please go ahead.
I'm sorry?
Yep, you were talking something.
Oh, no, I was just going to say, yeah, I'm having my coffee with cinnamon. my favorite.
Sure, sure. So I think this was really very insightful session, and you have already been inspiring a lot of Indian kids. So this was really a good session. So hope to have more such sessions. So thanks a lot, and
Sure.
have a nice day ahead. So whatever questions we have, whatever we could not ask, so maybe I will interact with you later on for the same.
Absolutely. Yeah, I'd be happy to.
Yeah, sure. Thanks a lot. Thank you.
All right. Thank you very much.
Thank you.
Thank you,
Have a
George.
great day.
Thank you.
Oh yeah, I forgot. Serena was also there. Serene, sorry.
Hi.
Yeah.
Thank
Hi.
you so much.
Yeah. So maybe we will interact again soon.
All right. Thank you.
Yeah.
Y'all have a good day
Thanks.
or the rest of the day. Bye-bye.
Sure.
Thank you,
Yeah.
George.
Bye.
Bye.
See you.
Thank you.
Bye.
Bye-bye.
Good night.